In this video, I will solve so-called a contribution game. So in this problem, we have it's a standard problem for intermediate micro class or for game theory class. In this problem, we'll have two agents who co-own a business, and they own it in a 50% shares, so equal shares. So the profit of our agents will be big in effort levels. So E1 and E2 is effort levels, and the profit that the business generates as a function of this effort levels is given by this function here. So it's contribution of the first agent plus contribution of the second agent multiplied by some constant. So here it's 6 plus what can be called a synergy term. It's an addition where when both agents contribute positive amounts, then the total revenue further increase because they just two heads are better than one, essentially. That's the logic of this synergy term, synergetic effect. Now each agent has a personal cost of effort. They're symmetric in this problem, and so let's start solving it. We will start by solving for the optimal effort levels when both agents work together, so they don't try to free ride on each other or anything like that. They just actively will be finding optimal effort levels when both agents act in their joint interests, so to maximize the payoff that they take home. Okay, so how we can solve this? Well, then the problem is quite easy. We just maximize the total profit. So 6 E1 plus E2 plus 1 E1 2 minus the total cost of effort. And we want to maximize it with respect to E1 and E2 at the same time. So that's what will be different from when the agents start acting in their own interests. All right, so to maximize, we just need to take first order conditions here. So for E1, it will be 6 plus 1/2 E2, 0 minus E1. So equals to 0, and same condition for E2. C2 equals to 0. Now, since the equations are symmetric, we know that optimal levels will be the same. So we can just solve for them. It will be 6 plus 1/2 E minus E equals to 0. So 6 1/2 E, therefore E1 equals E2 equals 12. So the optimal effort levels when the agents act in their joint interest, maximizing the total welfare created, profit minus the cost, is effort levels of 12. So when they do it, we can calculate profit to the firm. So it's when both agents act 12. So it's 6 times 24 plus 1/2 12 times 12. So that's 144. Half of this must be 72. So that's also 144 plus 72 must be 216. 216 looks correct. So that's the total profit. Now in individual utilities, so utility of agent 1 will be 50% of profit, so he gets 1/2 of 216. And he expends a cost of 1/2 times 12 squared. So that's 108 minus 72, which is then 6.8, 36. 36. Obviously, utility of second agent is also 36, and total welfare created, well, we call it total welfare, social welfare, is the sum of two utilities here. So that's 72. 36 plus 36. Okay, so this is the numbers that we will, let me reserve them here at the corner. So E1 equals 2 equals 12. U1 is 36. And U2 is the same, and total welfare is 72. All right. Now let's actually solve a game theoretic problem where both agents act in their best interest, and solution concept that we use is a Nash equilibrium. So then we need to set up a payoff of the first player. So his payoff will be kind of utility of the first player as a function of effort levels is half of the profit minus his cost, which is this. And half of the profit will be 3 E1 plus E2 plus 1/4 E1 E2 minus 1/2 E1 squared. So now our agent will maximize this, taking E2 as given. So our first order condition will be, so we take derivative with respect to E1, we'll get 3 plus 1/4 E2 minus E1. So we set it equal to 0, and we get ourselves the best response of agent 1 as a function of E2 is given by, so we put E1 on one side, everything else on the other, so it must be 3 plus 1/4 E2. So note that there is no corner conditions here of any kind, because even if the other agent picks level of 0, you want to produce at least 3, and as the other agent contributes more and more to the firm, your contribution is also growing. So it's an upward sloping best response function. So that's a full best response. Obviously, if we solve for the second agent, his best response will look identical. So once we get best response functions, we can calculate Nash equilibrium. So its Nash equilibrium will be given by a system of conditions where E1 equals best response of from 1 to 2, so 3 plus 1/4 E2, and E2 equals to 3 plus 1/4 E1. Again, we make an observation that in equilibrium effort levels will be the same, therefore it must be 3/4 E equals to 3, therefore 1 E2 in equilibrium will be given by 4. So this is a solution to this equation here. Okay, so we can see quite a difference between when agents act in their joint interests and contribute, each one contributes 12. If they act in their own interest, maximizing their own payoff, then instead of maximizing the overall thing, the size of the pie, they will be picking much smaller level, just at level 4. So let's calculate the resulting characteristics. So the profit of the firm then will be 6 times total effort level, which is 8, plus 1/2 product, which is 16. So it's 48 plus 8, that's 56. So profit dropped by a lot, 4 times almost. And now individual utilities, they will be the same, but nevertheless. So each agent gets half of the profit, so you get half of 56 minus the cost of your effort, and your cost of your effort is half of the square, so it's half of 16, so minus 8. So 56 by 2 must be 28 minus 8. So utilities are just 20. So obviously U2 is also 20, and total welfare now is 40. So we see that once agents start acting in their own interest, together they lose 32. Okay, so that's the end of for an Nash equilibrium part. And finally, we will solve the same problem, but with an additional condition that, let me erase this part. So let me copy our answers. So in Nash equilibrium, we got 4. We got utility at level of 20, and total welfare we got at 40. And the last part of this question will be government is going to introduce a revenue tax at 20%. So 20% revenue tax. So effectively, what agents are going to keep is they earn some profit. So basically, our revenue is this pay function. That's what we will call in this problem. We call revenue because our costs are not for the firm. Costs are for the effort level of the agents. So 20% is on this quantity. So each agent gets to keep it earns only half of the profit, and for this profit, he will actually be only getting keeping 8 out of 10, so 80% of this. Okay. So now let's set up the new problem. So utility level of agent 1 as a function of 2 input levels will be 1/2 times 8 over 10 E minus his individualized costs. Which is plug in profit, so 0.4 of 6 must be 2.4 E1 plus E2, and plus 0.5 is just 0.2 E1 E2 minus 1/2 E1. Now each agent will be maximizing this function instead, so his pay from the effort has been reduced. So first order condition, we will get 2.4 plus 0.2 E2 minus E1 equals to 0. So in this problem, our best response of agent 1, the function of effort of agent 2, will be 2.4 plus 0.2 E1. Obviously, best response for the second term will be given by a similar expression. Of course, taxation is symmetric. And now if you solve this system for Nash equilibrium, you will get 3. Okay. If I plug 3, I can see that it will give me exactly this number. Okay. So intuitively, what happened? Well, once government introduced the 20% tax, agents further reduce their effort because they are not getting as much profit anymore. Obviously, if government, let's say, decided to take 100%, then effort levels would drop to 0, because there's no point in working then. So E1 equals E2 equals to 3. So let's calculate the profit. So the profit at these levels will be 6 times 6 plus 1/2 of 9. So 36 plus, so it's 40.5. So notice that tax revenue, so let's calculate tax revenue. Tax revenue will be 20% of that. So 20% of that is, so 40.5 times 0.2 is 8.1. Okay, yeah, just divide by 5. That's correct. And then utility of agent 1 will be half of what's left, 32 point. So it's 1/2 of 32.4. Let's say what's left after tax minus cost of equity, which is cost of equity will be 9. So if you do the calculation, you will get 11.7. And the same for U2, 11.7. So we see that utilities further reduced from 20, and they are reduced from 2 sources. First of all, you need to pay a tax, so you're getting less. So you would get less, even if you keep reducing at level of 4, your utilities would have come down. But then on top of that, you reduce your effort levels. Most agents reduce it, so there is even less money on the table. So the pay is taken as a hit. And now total welfare here will be, of course, utilities U1 plus U2. But also actually tax revenue, we cannot exclude it. It's still being generated, it just goes to government. So we have to add tax revenue here. And for the total of the 23.4 plus 8.1 must be 31.5. 31.5. Okay. And we can compare, so total welfare here is 31.5. So we can see that loss relative to this case, relative to 40, is 8.5. This is the extra loss due to government taxation, additional loss. And this comes totally from agents reducing the effort levels. Because if you just tax and money goes to the government, it doesn't reduce economic pie, right? It's just reallocation of resources. But the fact that agents do reduce their effort levels is what generates this extra loss. So that's it for this problem.